In this section, we're going to look at the background theory behind UV visible spectroscopy. In this section, we're going to look at the instrumentation that is used for UV visible spectroscopy. So we're going to have a look at the components that make up the instrument and how these work together to give you important information about your sample. Okay, so the basic principle that underlies spectroscopy, any type of spectroscopy, is that it relies on the interaction of electromagnetic radiation with a compound or molecule of interest. Typically, in pharmacy, we're looking at organic compounds, so compounds containing carbon, hydrogen, nitrogen, etc. Now, the diagram that you can see on here is the electromagnetic spectrum. Now, this can be represented as a wave going from a long wavelength to a short wavelength. Now, the wavelength is the distance between these peaks, and you can see that as we move to the right, the distance increases. Now, as our wavelength increases, the energy that those waves contain decreases. So you can see on the scale down here, we have radio waves on the far right with wavelengths of centimeters to meters to even hundreds of meters. And as we move to the left, as we increase our energy and decrease our wavelength, we move into the infrared, the visible light, ultraviolet, then through to really high energy radiation like X-rays and gamma rays. Now, UV visible spectroscopy and infrared spectroscopy use light that is within the ultraviolet to visible to infrared regions of the electromagnetic spectrum. But it is possible to get types of spectroscopy that rely on the use of X-rays or gamma rays as well. Now, as I've said, we're interested in the UV, visible and infrared regions of the spectrum. So within this, the UV, the ultraviolet, is the highest energy, so the shortest wavelength, and starts around 200 nanometers and goes up to around 350 to 400. And there we get into the violet region of visible light. Now, the visible spectrum goes from around 350 nanometers, which starts off in violet light, moving through the blue, the green, the yellow, and into the red. And the red maxes out a little further than is on this diagram. It goes up to around 800 nanometers. That's when we're really on the borderline of infrared light. So within UV visible spectroscopy, we're interested in using light that's in the ultraviolet and the visible region. And in infrared spectroscopy, we're only using light that sits within the infrared region. A UV visible spectrophotometer is actually a pretty basic piece of equipment, and it has quite a simple layout. Now, it starts off with a lamp, which you can see here. Now, this lamp can either produce visible light or UV light. And if it's producing UV light, then we have what's called a deuterium lamp, but visible light is given by a tungsten lamp, very similar to the lamp that you would find in a car headlight. And if you think about this a little bit, it makes sense to use a car headlamp bulb as a source of visible light. Car headlamps are optimized for producing very large amounts of visible light to allow drivers to see. And so they're sources of quite intense light. Now, when the machine is turned on, the bulb turns on and it emits either UV or visible light. And this light is then passed through a slit. Now, what this slit does is it narrows the beam of light that comes out and makes it small enough to pass into something called a monochromator, which you can see here. Now, a monochromator is something that splits light into its individual wavelengths. So imagine visible light entering a prism. You know how it's split into a rainbow. Well, each of those colours has a different wavelength of light. And so that is what this monochromator does. It splits the light into the different wavelengths. And by rotating the monochromator, we can select which wavelength then comes out of a second slit and passes into our sample. Now, the light that goes into our sample is called the I0, or the incident light. Now this light enters into the sample, which is typically a solution, and it's a solution held in a cuvette that can be made of special plastic or quartz. Now both specialized plastics and quartz are very good at allowing large amounts of light to pass through them. So we take our light that goes in, so our incident light, and then out the other side of the sample we get our transmitted light, which is called IT. This light enters into a detector where the intensity of the transmitted light is compared to the intensity of the incident light. And this is what gives you your absorbance reading. So we get an output of intensity versus wavelength. And because we can move the monochromator, we can scan through lots of different wavelengths very quickly. Now there are two types of instruments. We have a single beam instrument, which is what this diagram is showing. So we have a single beam of light that passes through the spectrophotometer, through the sample to the detector. Now the downside of this instrument is that we have to first blank our instrument, so put in a cuvette that contains our solvent, so it could be water or an organic solvent, into the machine and measure the absorbance of that before we measure the absorbance of a solution containing our sample. Now a double beam instrument splits the light in two after it comes out from the bulb. So we have a beam splitter that would be here, and you have two parallel beams of light that then go through and get recombined before they go into the detector. Now, the only advantage to a double beam instrument is that you can record from both a reference sample and your actual sample at the same time. So it makes the collection a little quicker. Now, if you return to Blackboard, you'll see that there is a YouTube video embedded in Blackboard for you to watch. Now, this video shows you the inside of a UV visible spectrophotometer. Now I've put the link here just in case you have any problems with the embedded version on Blackboard. So you should go and review this video next.